Hello and welcome to the deep learning course. Apart from the NLP field, we will be focusing now across the convolution neural network and respectively we'll be passing through the fundamentals of the convolution, and we will be creating another course for the intermediate fields topics across the NLP and the convolution as well. So let's get started. Basically, by the appearance of images data across social media fields like Twitter and Facebook, etc., we have a demand of determining or extracting new information from such data as we do through the text data. By the appearance of large amount of images data and the lack of architectures to extract from these images some helpful information like the linear layer and the LSTMs or NLP neural networks. This was a huge lack of research, and data drives research. Okay, so after this appearance of data, like if we apply linear layers, why we cannot apply some simple linear layers to this images data? Basically, if I agreed to use linear layers, it will be needing to have understand how the machine will observe this image. Okay, so the machine actually observes this image as nothing but a matrix of numbers. If this image is a grayscale image, then it will be a matrix of pixels. Each pixel will be determining whether this pixel is white or black, and anything between them, this will be between 0 and 255 value. And after generating this matrix, or after passing this matrix to the neural network, the neural network will need to pre-process this matrix to, first of all, to flatten it, and flattening will require to make this matrix into a single dimension in order to pass it to the linear layer. And the problem is, if this image is 1,000 by 1,000 dimensions, so the matrix will be holding a 1 million value, and this flattening will be a lot expensive. So that's one of the main issues of not using the linear layer. Because if you think about this image, for example, you see a huge area here that is basically redundant. Regardless of high quality image or anything, I don't care about what is this part about. I just care about the cat. Okay, I need to classify whether this image is a cat or a dog or a giraffe or anything else. So I don't care about all these background areas. I need some architecture to only focus on the crucial features from the image and make them propagate through the network, so the final layers can understand the most important distribution of the features. Okay, and neglect or cancel out the background or the non-important to across with respect to the downstream task that I'm working upon. Another issue with the linear layer is it depends on the order. Okay, the order of the input matters. So if this image is a little bit translated from this to this, so it is a small translation, but the core features of the image are still retained within it. Actually, with respect to the linear layer, this is a drastically huge change because the order is pretty much changed a lot from this data. Okay, and changing the order will be forcing the linear neural network to learn the distribution of a different image. So the linear layer cannot understand that this is the same image, but it will be considered as a different image. So that's another bad disadvantage of the linear layers. So what is the next architecture? We need to reduce the number of parameters as much as possible because this is a huge redundancy in the memory. And we also need to focus only on the crucial features and make them propagate through the neural network. After this, Yan LeCun, one of the pioneers of the convolution neural network, have invented or developed a new architecture, which is one of the earliest architectures within the convolution neural network field, which called the LeNet, and it basically was 5 layers of convolution. So we will be now discussing what is this convolution is. Basically, the convolution is nothing but passing a two-dimensional matrix, which is a small matrix called kernel, and passing it through every part within this image and extracting from these parts what is the most important features within each of these parts. And it will be trying to reduce the size of this image and retain only the crucial features, propagating them, making them flow to the end layers. So that's the main objective of the convolution. This kernel will be passing across all this image and trying to generate these most important features as much as it can. Okay. And by the way, this kernel is the only learnable parameter on the convolution neural network. So the convolution will not be learning anything but the kernel values. And it will be try to optimize these values in order to capture out what is the most important features out of this image. Another simple example here, like this kernel movement, it will be moving across all the image and extracting from each part of it a value, and this will be creating another image which will be called, which we are calling the feature map. So the input image, after passing through, after applying the convolution across it, the output of it will be called the feature map. Okay, another way of looking at it actually is, as you can see here, we have much of redundant information across the head of the cat. And if you can see here, the feature of eyes and the feature of the nose and the mouth of the cat are pretty much salient here. So they are more appearing more purely than other features. Also, the ears of the cat have been exposed more in this another layer of convolution. So as you can see, as we can go deeper with the convolution, we are extracting the most crucial features. And this is actually a pretty much critical part, because if the convolution didn't capture all the crucial features, this can be indicating an overfitting of the network. Okay, because for example, if a small dog will be having a similar feature with these eyes and this nose, so the neural network will can falsely and incorrectly can be predicting a cat instead of a dog if it cannot capture, for example, the ears shape. Okay, so convolution will be a critical part. The kernel should be actually extracting all the critical information, and this is what is the objective of the neural network, is to maximize the number of features being extracted as much as possible and to reduce the redundant data as much as possible. Okay, another way of visualization is this. For example, this image here is a dog, and as we pass deeper through the convolutional layer, this is the convolutional layer, and after this is the fully connected layer, which would be final layer to predict or to classify that this is a dog or a cat. So after passing all these layers, as you can see here, the most crucial features is being exposed or being salient, and the other features will be suppressed. and this is not important. We only focus on this. Okay. Also, if you can imagine, when you look at something, you only look at this thing. You don't look at the background. Okay. When I look at the when I look at my image, I don't look at anything else of the screen. Okay. So that's pretty much similar to this concept. Okay, because the convolution is being from the concept of the retina on the eye, and we will not be discussing the details, but it's also taken from this part. Okay, and as you can see here, the fully connected layers is being translated to the last layers, because this will be the convolutional part here will be extracting for it the crucial information, the crucial features, and then we will be flattening the last convolutional matrix to be inserted to this fully connected layer instead of inserting the original image with all its redundant data. So now a small change in this image will not be affecting the linear by the linear layers by a huge change. Like the linear layer can now be learning the distribution of this image with its only important features. Okay. Now let's start by a full example with the convolution. Basically, this image is 15 by 15, an example, and we will be applying convolution on it using this kernel. This kernel is a simple kernel to extract the vertical edges. Okay, and this star, it will be corresponding to the convolution process, and it will be nothing but a dot product. Okay, so we will be multiplying this one by this 36. For example, this is the first it will be called the receptive field. It will be the first receptive field in this area. By putting the kernel on the image, this will be called the receptive field, and this 36 will be multiplied by 1, the 0 will be multiplied by 14, and 16 will be multiplied by -1, and then plus adding them all, 19 by 1, 30 by 0, 42 by -1, multiplying them will be and adding them all will be generating a single value. So the output of this kernel of this receptive field will be a single value, and this will be inserted into another matrix which will be called the feature map. Okay, as you can see here, these 9 values have been reduced to a single value. So that's why the data or the image shape will be reduced as much by propagating more and more across the convolution layers. So as much as we go deeper, the size of the image will be reduced step by step. Okay, so the value of the output value of this kernel will be 5. The output product of all these numbers by this matrix, by the kernel values, will be 5, and etc. will be passing the shape of this matrix will be 13 by 13, which will be calculated from this equation. N is nothing but this 15, the number of the dimension of the original image. K is the kernel shape, is the kernel dimension, which will be 3. B is the padding. We don't have any padding here in this image. Padding is nothing but adding zeros at the upper on the around this image, and this padding will be actually saving the dimension of the image. If I don't need to reduce the image dimension, I can add a padding here, like zeros around this image, to avoid reducing the dimension of the image, because the kernel now will be multiplied by zeros, and in that case the dimension of data will not be reduced, so that can obtain also 15 by 15 as a feature map. Okay, so that also called the padding the same. The same padding is while implementing this in the code, you can observe that I can add a parameter called padding with same argument, and this will be retaining the shape of the dimension of this image or the previous feature map. And S is nothing but the stride, which will be the steps or the movement, how I'm moving. Like if the stride is 1, I will be moving 1 step ahead or 1 pixel ahead, moving this kernel 3 by 3 on the right. And if I'm going down, I will be passing only this to this 3 and take 1, avoid this first row. Okay. And this is, as we have discussed, this is the receptive field from the image by applying the kernel accuracy. Another layer called the max pooling, which is also reducing the shape of the feature map or the shape of the previous image, the previous matrix, by the same equation of the convolution. The max pooling will be also creating another feature map, and it have its own parameters, but it doesn't have any learnable parameters. Like it is only reducing and evaluating the maximum. For example, it is called the max pooling because applying this kernel on this receptive field, it will be generating a single value from this matrix. So this matrix is 4 by 4, and the output of this matrix, the output of this receptive field, or applying this kernel on this part, it will be the maximum value across all these 16 value. And if the stride is 3, then I'll be moving by 3 steps to the right and also to the bottom. So as you can see here, we are moving with the huge steps, like 3 steps. So the equation of the output, it will be dividing by 3. So in that case, subtracting from 15, this 4 will be 11, and adding 2, it will be 13 over 3 plus 1. It will be plus 2 by 0, it will be neglected, and the output will be 5 by 5. So as you can see, the dimension is reduced by huge as we are increasing the step size or the stride. So the stride will be affecting the dimension of the feature map with a large weight. Okay, so keep that in mind by implementing the output. We need to keep track of the dimension of the last output of the convolution. So just keep this equation in mind as we go into the coding part. So after this, we will be applying the pooling process. So as you can see here, first we apply convolution, and then we have produce this feature map. And after this, we'll be having the max pooling layer, which will be also reducing the output of the feature map and generating a more purely features than the convolution. Also, to visualize this is an example of a convolutional layer with an 8 kernels. As you can see here, the repeating of the dogs with 8 images concatenated together. This is nothing but it is not a single kernel, but it is 8 kernels being multiplied by the image, and then we will be regenerating 8 feature map correspondingly. Also to be noted here that the convolution is a parallel process, not a sequential process. Like if I have these 8 kernels, I can apply them at a single instance using a GPU, for example, and each kernel will be applied by an instance. And in that case, the output will be produced at once in a parallel fashion. So the convolution have this beneficial advantage, like it can be applied, it will be enabling parallelism. Also, after this, we'll be applying the pooling on the convolution. And here, as you can see, it will be increasing the large value and eliminating the small values. Like some smoothing or some not pure features can be removed from the pooling. Okay, and only the main features can be retained. Okay, like for example, the eyes from this matrix have been removed, and that's why we need to apply multiple kernels, because sometimes the kernel will be removing the salient features or the crucial features. Okay, so that's why we need to apply multiple kernels, and keep learning these kernels and making the output propagating across another kernels also. So this will be the learning objective of the model. As you can see here, the difference between the pooling and the convolution, that the pooling will be generating the only the maximum, or generating the main core features and propagating them across the next layer. Across multiple features, like for example, if I have 100 kernel instead of a single one, I will be also having a 100 feature map, each of which will have a different feature being shown, as you can see. So each kernel will have different numbers, and this is the learnable weight, and producing different feature maps, by which this feature map can be combined into a single three-dimensional matrix, which have a 100 as the third dimension, which is the number of kernels. And after this will be passed through another kernel and another max pooling layers. If we have a colored image, then in that case, this will not be a single two-dimensional matrix, but it will be actually three-dimensional matrix, as it will be having at three channels, the red, green, and blue correspondingly. And actually the image here, or the pixel, will not be a single value. The pixel will be a vector of three values. Each pixel will have three values, red, green, and blue, and their intensities or their variation will be showing us the last color. Like for example, orange is a combination between the red and green and blue, with corresponding weights, like increasing the weight of the red, etc. So these are actually the primary colors. Like any color is a combination of the red, green, and blue. So these three channels will be inserted to the convolutional layer, and in that case, these three channels will be a single three-dimensional matrix, and also the convolution process will be applied in a three-dimensional kernel. So it will not be a two-dimensional kernel, it will be the same shape of the input, and it will have three layers. Each layer will be multiplied correspondingly with the red or green or blue layer channel. And also the output feature map will be a single value, so it will be a two-dimensional shape. Okay, also here, for example, this is a simple elaboration of how the kernel will be moving across all these feature map. It will be applying every corresponding channel will be multiplied by the corresponding kernel channel. So the kernel will have three channels, and this will be dot product also across all these values through this kernel, through the image. After some time, a huge data set have been released, which is called the ImageNet. And ImageNet actually is a collection of 14.2 million labeled images, and they are having a 1000 class. All these images have driven a lot of research in the area of convolutional neural networks that we are going to discuss by now. First, some machine learning models have been applied, like the singular, the SVD, and some of the support vector machine have been applied, but they were having a huge error and low accuracy. And after applying the convolutional neural network properly, we have determined a low error rates. First thing, on 2012, AlexNet have been released, which was actually building a subsequent layers of convolution in manners like the input channel will be three channels, and the AlexNet will be passing them through 8 convolutional layers. And this will be again, and it will be reducing the number of the error rate drastically with a noticeable value. As you can see here, it is a combination of 5 convolutional layers and 3 linear layers, and it have reduced from 27 percentage error into 17 percentage error top 5. So top 5 is like they have determined this value as a model can be producing output of 5, takes the top 5 outputs from the model, and if the true label or the true class within these 5, then we will be adding this as a top 5 accuracy. This will be adding +1. So AlexNet have reduced the error from 27 to 17 percentage, which is a huge progress in the field of convolution. And here we'll be representing the convolution as a blue blocks and ReLU layer as the violet and max pooling as this tomato. After this, we'll be showing how the AlexNet actually builds the layer. So it is a combination of all of these 3 layers. First convolution, then ReLU, and after all the max pooling layer. And they keep repeating again and again this convolution, ReLU, max pooling, convolution, ReLU, max pooling, again and again until the last linear layers. So this actually, as you can see here, the number of kernel is increasing and the dimension of the kernel is decreasing. So basically it started from 11 by 11, then 5 by 5, then 3 by 3, 3 by 3, and 3 by 3. So the size is dimensioning, but the number of features or the number of kernels is increasing. So that's another notice that we can observe from. I have also created another slides showing how these values is being observed. So this is the first convolution, and after this we're applying max pooling with the 3 by 3, and as you can see here, this is the same number of kernel. This is 96, it is 11 by 11 by 96, so we have 96 kernel will be applied on this 3 channel image and generating 96 feature map, each of which will have the corresponding 55 by 55 as we have determined from the previous equation. And then we will using a 3 by 3 max pooling kernel. Actually, max pooling will not be having anything to do with the feature map, so the same number of 96 feature maps will be retained, and then we apply convolutional with 256 feature kernel, which will be generating 256 feature map, and also reducing actually the number of dimension is the same. As you can see here, we applied padding to these feature maps, previous feature maps. So as you can see here, the dimension have been the same for the width and height of the kernel, but the number of kernels have been increased, which will be adding how much variation, okay, and much information. And by scoring that this feature appeared, because by going deeper, we should be having, or we should be expecting the neural network to extract a more complex shapes, like the whole ear of the cat can be extracted. Okay, so I'm here reducing the size because I don't need large sized image. I need a small size kernel, but too many kernels. Okay, because this will be adding variation in order to extract most important features as much as possible, and cascading them across each other from the convolution feature maps. And after this, we will be adding max pooling, and it will be also reducing the size again. And after this, I'll be adding another convolution, which will be increasing again the number of features to 384 instead of 256. And then I'll be applying another convolution, which will be reducing the number of kernels again. So this is somehow a bottleneck. Like for example, I'm increasing and then decreasing again. So I'm trying to compress all the 384 feature map information into this small 256 kernel information feature map uh, matrices. And then applying max pooling, I will be reducing the output pretty much by 6 by 6, 6 by 6 into 6 by 6 matrix size, and the number of kernels within this matrix will be 256. So we have a lot of variation and very small dimension of the image, because features doesn't have to be large. Okay, this is the main assumption. Like I can check the eyes in a single 6 by 6 feature map, and this is passing through all the features of the cat, as you can see. And after that, we will be applying this linear layer, so it should be flattening these feature maps into linear, and the dimension of this will be 9216, and then another feature map where it will be 4096, and then another 4096 linear layer, and finally the last layer, which will be 1000 classifying by the softmax, and the softmax will be ranking with the highest class probability of the highest class, and we will be taking the top 5 or the top 1, and each of which will have another accuracy, top 1 accuracy or top 5 accuracy. And AlexNet have actually been huge popular. Like if you know, from the NLP field, we call the transformer the AlexNet moment of the NLP. So AlexNet is a pretty popular network in the convolutional area, and the development have been applying the same concept of Alex as we pass through the next concept. Another way of propagating the information, Google have released a new model, which is the Google Net or the Inception model. It is deeper model, as you can see, like it is pretty much 22 layers, and have reduced the top 5 error from 17 into 8%, which is a huge improvement. And the main idea of the Inception or the Google Net is basically why to choose which convolution or which kernel should I use. What is the shape of the kernel? Should I use a kernel of 1 by 1 or a 3 by 3 or 5 by 5, or apply max pooling at this step? Actually, Inception will be doing all of them at the same time. So as we have discussed before, like convolution can be parallelized. So all these feature or all these kernels can be all applied to the image and generating output correspondingly into a single feature map, as you can see here. But the most important thing that we need to consider with the size of the output, it need to be handled by which all the kernel output should be having the same size to be concatenated across. So as you can see here, the feature map of the 1 by 1, the feature map of the 3 by 3, 5 by 5, and the feature map of the max pooling, all of them have been concatenated together. Okay, if you can see from also the actual image here, this is a convolution layer, and we have here 1 by 1 and 3 by 3 and 3 by 3 max pooling. So these are being again combined to generate a new layer. So this is an inception module, which can be applying multiple kernels at the same time, and generating the output of them. Also, another way of it is they have applied a one-by-one convolution, because this will be reducing the number of features by much, like across, for example, 10 times uh, smaller, or 10 times reduction of the number of parameters needed by applying, instead of applying 1 by 1, 3 by 3, 5 by 5 max pooling, they apply 1 by 1 before the 3 by 3 kernel and 1 by 1 before the 5 by 5 kernel, because the output of the 1 by 1 is actually reducing the number of parameters greatly. In that case, like, this will be acting as a bottleneck also. I need to compress all these feature maps into a one by one convolution, so I need to convolve across all these by a single element. Also, some assumption calling the one by one is a linear layer, nothing but it. And anyway, in the inception module, this can be helpful in the reducing the number of parameters, because all these kernel filtration needs a lot of parameters to be computed. Okay, so one by one, the convolution, it will be reducing this by a huge number of parameters. After that, a new model have been released, which is the VGGNet, a very large scale neural network that is applying convolutional max pooling, ReLU max pooling, etc., etc., in also 5 layers, and passing them across each other. It also have released a huge area, a huge, a more better accuracy in terms of the top 5 from the ImageNet competition. And after generating this, somehow analysis of a new neural network have been appeared, but it showed some analysis, like, because all the research was in the direction like getting deeper is getting better, and this analysis shown that when we get deep neural network, the training of the shallow neural network is from the first epochs getting a huge loss reduction. So it is learning a lot from the first epochs, while for the deep neural networks, it will need a lot of epochs to learn. Why is that actually? Like, why we need all these epochs to be learned? In order to learn a simple neural network can learn quickly. So why deep neural network cannot learn it as quickly as a shallow neural network? Basically, if we have these set of layers as a deep neural network, so each layer here we will have a weight matrix, and the initialization of these weight matrices is pretty much random. Okay, so the input image here, while propagating through all these subsequent matrices or all these subsequent hidden layers, the information will be pretty much lost through this several multiplication of these layers. So as we go deeper and deeper, the actual information of the image will be removed totally as we reach the last layers, and the output in the same way will have a loss. So the gradient will be propagating to the same path. In that case, the gradient will be also lose its information while getting vanished until it reached the early layers or the beginning layers. So that's why deep neural networks suffers from this learning. Like, it will need a lot of epochs in order to pass this information and to tune these weights in order to propagate the correct information of the image till the last layers and propagate the gradient to the early layers. So the data propagation and the gradient propagation are one of the top issues for the deep neural networks. And after this, skip connections have been evolved. What is actually a skip connection? It is nothing but allowing the flow of the information. For example, if this is the input image, okay, and after this we'll be passing by a first hidden layer, then another hidden layer. In that case, I can pass also the same input information to the second hidden layer, skipping the first hidden layer. Okay, so the second hidden layer accepts the previous hidden layer, the first hidden layer output. And instead of this, I will be just adding the original input of this first hidden layer to the second hidden layer. So the second can be informed with what was the input, and also it is a quicker flow of information to the forward layers, like the end or the last layer can also have this. It will also call the highway network, because the information flow from the highway instead of flowing in these sub layers, passing through the layer and layer and layer again. The information will be flowing through this another highway in that elegant way. And also the neural network can determine by if it decreased the bias of this hidden layer, so it can cancel out what is this layer outputs and only consider the input layer. So if it have reduced the bias of this linear layer by much, so it will be pretty much negative value. So the ReLU will only consider the positive value, and if this is negative, so it will be zero, it will be neglected. And actually only the ReLU of the X will be determined, which was the original input. So this is how the neural network can achieve this flow or fast flowing of the information from the input to the subsequent layers. So getting back to this original layer, we have here broken down the layers of the deep neural network into blocks, and applying this skip connection at the end of each block. Okay, this actually have introduced somehow a modularity, like the network can be divided into modules, and these modules can be learned through or being skipped. And this gives the strength of or the power to the neural network to increase its size, and by the same way I can avoid removing or avoid loss of the information being passed through and passing them through this highway or the skip connection. Okay, also the back propagation of the gradient can flow on the same way, on the same highway path, like the same skip connection path. Okay, so the ReLU of H3, it will be the ReLU of X plus H3, and I can skip all this block, all this module, by reducing the bias of this H3, so the ReLU will be only applied on the X. This network actually is called the ResNet, or the residual neural network, or the skip connection neural network, or the highway connection. One of the main features, like it is a faster flow of information and a shorter path for the gradient to flow, and also adding this modularity as we have discussed. Like I can add more blocks and getting deeper neural network and stronger, because the neural network can determine whether to use this block or cancel it out. Okay, so that's an elegant idea actually, and a simple, very simple idea. We can apply it through the code as we can see earlier in the next tutorial. This is another image from the research, like the skip connection can be applied across multiple hidden layers. Each block will be sending the information to the other blocks and flowing the information in that elegant way. This is an example of a 34 layer of ResNet layer, and showing how the information passes across these layers. This is the last part of our lecture today. Hope you understand the fundamental parts of the convolutional. And next part will be applying some coding on this using the PyTorch module. See you there, and thank you. Happy learning.